Hello, everyone. Today, we will be talking about audio and video analysis. I'm Carlo Giacometti, and me and my colleague Ali Hashmi will present the new developments in this area. We both are developers in the standard vision team for Wolfram research. The main topics that we'll be talking about today are improvements in speech recognition, audio analysis, updates on video, image analysis, updates on video, a new function used to visualize results of analysis called highlight video, updates in object detection on images and as a consequence in video, and multiple object tracking. In version 14.1, the backend for speech recognition was switched to Whisper. Initially, we were using a pretty old neural net called Deep Speech 2 that was getting more and more outdated. With this new backend, we gain a lot of things. We gain speed, we gain quality, we gain language support. It has been an overall gigantic improvement. You can see speech recognize works exactly as you have been used to. You pass it on the object and it spits out some result. So first of all, what is Whisper? Whisper is a neural network that was developed by OpenAI. It is based on transformer blocks, which is the technology that powers most LLMs, large language models. And this is kind of an application of that technology to audio signals, which was, I think, one of the first that was this successful. So what happens when you pass this network on the object? Well, first, it is split into 30-second segments. It is encoded as a Mel spectrogram, which gives information about amplitude and frequency content of the signal. And it is encoded into a tensor using transformer encoder blocks that use self-attention. You can see this is the encoding part of the network in this diagram from the Whisper paper by OpenAI. So we go from an input audio to a tensor that represents something that is semantically relevant to the words spoken in that recording. Now we need to decode this, and this is performed using transformer decoder blocks that use cross-attention, so they can pay attention to the previous tokens and the encoded data at the same time. Talking about tokens, which is what the model outputs, there are special tokens that can be included at the beginning of the transcription to steer the decoding. In this case here, you can see kind of a diagram that shows different types of special tokens in yellow that tell the model what to do for the next decoding steps. You can tell the model what language the input is in, or you can tell the model to automatically decode the language. You can tell the model to transcribe or translate, and we'll go more in detail about that in a second. And you can also tell the model to include timestamps corresponding to where specific segments of the audio were spoken. Once you get your sequence of tokens, you decode those and into a string, and you can then just end up at the usual results that you expect for speech recognize. There are massive improvements in quality with this version of speech recognize compared to previously. Here I have a clip of Martin Luther King's speech, and I can show you the comparison of the output of the new speech recognize, which looks excellent in my opinion. I just did an excerpt of the old speech recognition that we used to have previously, because it is also very slow. And you can see there are mistakes, there is no capitalization, there is no punctuation. So the quality improvement is, in my opinion, pretty gigantic. As I said, now we have punctuation capitalization. You can see here a comparison of the old result with the new result. We get a massive improvement in speed as well. On an Apple Silicon machine, the speech recognition moves at 65% the speed of the, is 65 times faster than real time. So about a second per minute of audio, while the old method was doing about 30 seconds to decode 1 minute of audio. So massive speed improvement. And it supports transcription in a pretty extensive variety of languages. The quality varies language by language, with obviously English being the one that performs better given the amount of training data, but all of these are supported. So the basic uses are pretty intuitive. The main one, give it an audio recording, it will return a string. The second argument tells a speech recognize how to subdivide a transcription, either by sentence or word or other kinds of type of segmentation. And then you can return different properties. And one interesting new property are the time-based properties. In this case, this one is called interval. And you can see it tells me that this bit of sentence happened between 0 and 5 seconds. Now, these intervals are, generated by the neural net, so there is no guarantee of them being accurate, but they are, and it could be a very useful addition to speech recognition. And you can automatically translate an audio signal from an arbitrary language to English. So I'll record something in Italian. Buongiorno, oggi è giovedì. And somehow wasn't happy. Buongiorno, come va? Yeah, so we can only translate to English. This is a limitation of the neural network itself, but this could be an interesting improvement in some workflows. Another side effect that we get from using Whisper as a backend is that we know we can detect which language is being spoken in a recording. We can do this through classify of spoken language or language identify, both. This has been integrated into video transcribe, which is a new function that automatically performs speech recognition and injects the result of that into a subtitle track. So here we have a video that contains just an image and then the audio track of the speech that we listened at before. Using video transcribe, we can inject a subtitle track. On this promissory note, insofar and you can see there are subtitles now in that video. Another addition has been adding styling of subtitles. So in this case, I am changing 63 is not an end, color but a beginning. Subtitles, but this accepts a lot of style specifications, and not limited to color, including font size, font style, etc., etc. Talking still about audio analysis, a lot of audio analysis functions have native support for video. Before you had to extract the audio track and then apply the audio function onto the resulting audio object. In this case, we just apply these functions to the video itself, and you can see the spectrogram, the audio plot, and in this case, the loudness of the first audio track of that video object. Speech recognize has been improved and has support for video directly as well, audio identify, and the list is pretty long and extensive. Most of the audio analysis functions that we have in the system now support video. Similarly, we wanted to have image functions also support video. In previous versions, I think it might have been version 13.3 or 14, we had added support for video in image processing functions. So functions that take an image as an input and produce an image as an output. In this case, if you do color negate to a video, it just applies that function, in this case, color negate, to all the frames, and the video itself is produced. In the new version, we are adding support for a lot of image analysis functions as well. So by that, I mean functions that take an image as an input and have an arbitrary return type that is not an image. One example of such function is find faces. This, for each image, returns a list of frames as an output. And in this case, the output is then packaged as a time series. So you can look at it whatever time, and you'll see the bounding boxes, in this case, for the faces present in the video at that time. Another of such functions is image key points. This returns a list of points, and you can see how this returns a time series as well. Yep, then this is a list of image key points at time 2 in that input video. This lends itself to post-processing these time series as well, to compute statistics over the video, etc., etc. But one new function that we added to streamline workflows stemming from this is highlight video. So we want to take a video as an input and give a highlighting specification very similarly to highlight image. The difference here is that this highlighting specification doesn't need to be static and applied to the whole video. It can be dynamic and changing with the advancement of time or frame to frame. So in this case, I am using a time series that was produced in the previous slides by running find faces on this video and just highlighting that. And you can see how that highlighting works seamlessly without any need for extracting data and mangling that data in a format that would be more complicated to deal with. Obviously, you can do static highlighting like you would do in highlight image. In this case, I am just displaying a disk, nothing very exciting. The highlighting can be time dependent, and you can specify what highlighting happens at which interval of time, but you could also specify a single time, and in this case, only the frame that overlaps with the single time will be highlighted. And you can see here, we start with our familiar disk, and in this specific frame, the second disk is highlighted properly. And as we've seen with the previous example, that time-dependent specification can be a time series. In this case, it's the time series that I generated using image key points. Or like in highlight image, you can specify a function, and that will be applied to the input image. Similarly, if I specify a function, that will be applied to each of the frames. And in this case, the result of it will be highlighted in the video. We obviously want to be able to style different highlighting with different styles. And like in highlight image, all of the styling and background and foreground specification will work. In this case, same kind of timed specification that I used before, intervals of time and styled graphics primitives. And you can see how the first disk is yellow and the second one is blue. And this styling works, even though this construct is kind of odd, right? Displayed on its own, once it goes into highlight video, this style is appropriately mapped on for each of the highlighting spec being outputted from the time series. So if I wrap time series in style, And this is the same time series with the key points that we've seen earlier. You can see how that start specification was respected. Another thing that was improved in this version was a new backend for image cases, and all of its related family of functions that perform object detection on images. And the output should look exactly the same, but the quality of the output should be superior. For example, if we compare the legacy method with the new method, you can see the new method on average has more positive detections. The number of classes is the same because it's trained on the same data set, but the number of boxes detected is higher. It can now run on GPU on Mac using the ONNX evaluator. And you can see that the timing is dramatically faster. So this is a big quality of life improvement. And all of these also support video as well. So if I pass the video, it will output a time series like all the previously mentioned analysis functions. And these, for example, this is image bounding boxes, and at each step of the time series, we'll get an associations with the results of the bounding boxes. And that result, as we've mentioned before as well, can be passed to highlight video so that items can be highlighted in a video in a time-dependent manner. So say that we detect these bounding boxes in a video using image bounding boxes. We have a bunch of rectangles, so we see automobile as a bunch of different bounding boxes in a single frame. What if we want to follow a specific car or a specific item in this with these detection results? Well, this is what multiple object tracking is about, and I will pass the mic to my colleague Ali Hashmi to briefly talk about this. Ali, if you want to start sharing.
My name is Ali, and I'm a developer at Wolfram Research, working in the sound and visions team. I'm quite excited to present to you about the algorithm on which our efforts are based on for integrating this new tracking functionality that is upcoming in version 14.2. So the topic, as Carlo pointed out, what if we are interested in tracking a specific object or multiple such specific objects? So the topic that the title is multiple object tracking. Why not single object tracking? The thing is, single object tracking is very easy. So you detect an object in one frame, another frame, another frame, and that is actually both the detection as well as the tracking happening at the same time. But imagine if you have like a scenario in which you have multiple a crowd of people walking in a subway station, and if you want to track a particular person, there needs to be a specific way of doing it. So multiple object tracking is just tracking a set of objects which we can identify from images and videos. And these are not just images and videos, but since we are mainly concerned with videos and images here, so the tracking that I'm talking about is in context of the image and videos. So when you detect these, the path of these specific objects, as you can see over here in this video, there is a lot of cells that are moving in a field of view, and you can clearly see that these have been tracked. So each of these tracks form a tracklet. Tracklet is basically just a container which contains the history of the object that you're tracking. Other areas where like tracking is really important is when you have, for example, self-driving cars or autonomous vehicles. Surveillance is another thing for military purposes, for sport analytics. For example, if you have to follow like players playing basketball in a field. Then in case of for scientific purposes, like from my own background, it was critical for us to be able to track different objects under the microscope. And it does not just pertain to the world of the very small, but also to the world of the very large that we can observe with the telescopes. Computer vision and robotics is another prime example where object tracking is really important. Yeah, so the idea I've already told you what tracklets are. So it's just a trajectory of the different objects, of uniquely labeled objects. So imagine if we have 3 objects over here, then and these set of points are representing objects and at different time points. Then if you are able to link these objects together, you form a tracklet. These tracklets can be contiguous, as over here, as you can see, for example, 3, 7, 11, 15, 19. If you can follow this is a particular tracklet. Or they can be broken. So over here, for example, 1, 4, 9, and somehow over here, you cannot link it back to the object number 18. And instead, some other track managed to join object number 18. So objects, as you can see, can get lost in a crowd or can be occluded or obscured by some other object. If some other person steps in front of you, then you're lost in the image or the video. So this kind of occlusion can be either permanent or temporary. And handling this particular issue of occlusion is really is a big challenge. And for example, I've already given you a quick example, that 1, 4, 9. And if there was a way to handle occlusion, then 9 could have been connected to 18. But for the purpose of the example, this came out to be a broken tracklet. So one way we can handle occlusions and deal with these subtle challenges is by using something which is known as a Kalman filter. So people who have a bit of background in physics or electrical engineering or any form of engineering, they use Kalman filters a lot. And Kalman filter is nothing but just a Bayesian scheme that enables us to make better predictions by integrating some measurements from the surroundings, from the different sensors. So imagine if this is the prediction that you're making of a car's location. This is the prediction. That's a pretty poor prediction. But and if this is the measured state, or this is let's say the actual state of the car, which is this red, then if we have some kind of a model if we integrate this measurement as well as our prediction, we would be able to get a better idea of where the state of the car is. So using these Kalman filters, we can handle occlusions and misses. So the algorithm that we are talking about is based on the original sort algorithm, and the original sort algorithm has been updated by using Kalman filters in a much better way to handle occlusion. And the linear motion model assumption has been used in this Kalman filter to deal with occlusions and nonlinearities for this kind of algorithm that we are using at behind for object tracking, which is OC sort, which means observation-centric, simple, online, and real-time. It's a very big name, but it's quite easy to follow. So what we do is in the first round, when we have, let's say, a given set of predictions given in magenta, and then you have objects that are being detected, shown in green, we want to associate our predictions with the detections. So one way is to look at how much of the predictions have overlapped with these green boxes. So how much of magenta is overlapping with green boxes, and using this and the direction in which the objects are moving. Using that, we can construct something which we call as a cost matrix. So it's a cost of association of associating one object to another, and it's given as a two-dimensional matrix. Then we can use some kind of an optimization solver, or we can solve it via some form of optimization. It's an optimization problem, so we have to minimize the cost and then have predictions assigned to the detections. So we use over here solvers like linear assignment problem, or you can use find independent edge sets or some other graph theoretic approach to solve the problems. At the end, what we have after end of round one, what we have is a set of paired detections. So things which have been successfully linked between magenta and green. But on the other hand, there are objects from magenta that could not be associated with the green over here. Or on the other hand, some detections that are green or are measured state, which could not be associated with the tracklets, which are the unpaired detections. So this is the first scheme, the first part of the algorithm. Then as I go along, so the second round is also quite easy to follow. So what we do is we try to find potentially lost tracks or reconnect any broken tracklets that are there. So by broken tracklet, I've already shown you that tracklets that were not associated or linked to any detections for the previous time step. So what we do over here is we create another cost matrix for the last bounding box that was ever linked from the remaining tracklets to the remaining detections that were not associated. And by doing this, we construct another cost matrix and do another optimization on the cost matrix. And then we get another set of pairings and unpaired tracklets, as well as the last unpaired detections. So finally, we have the successful pairings, and then we have the unpaired tracklets and the unpaired detections. In round three, which is very simple, is that we need to initialize new tracklets from the detections that remained unassociated even till the very end. And for the unmatched tracklets, we just remove or delete them if they have expired. So let's say if we consider that any tracklet that has not been associated for 4 frames or 3 frames is old, then we kill that tracklet off. But the interesting part of the algorithm is which makes it quite powerful, is that is what happens when we update the status of the tracklets. So if the tracklet is like contiguous, if it was already contiguous, and so what we do is we just get this measurement state, update our Kalman filter parameters, and then the detection on the green box is basically saved in the tracklet's history. But if the tracklet was initially not associated, but now it's matched, so what we do is we roll back from our predicted state all the way back to the last state, to the last bounding box, last match bounding box. And then from here, we do an update of our Kalman filter parameters. And by doing this kind of re-update, what is good about it is that any future potential future misses can be avoided in this case. So by doing this kind of a re-update scheme is what the authors of OSISort, by doing this kind of re-update, they managed to bring the efficiency up for the association part of the algorithm. So and the detection is then saved in the tracklet's history. So by doing several rounds of this, so we are able to kind of generate all the tracks, like whether there are thousands or hundreds of objects. So maybe I'll pass now to my colleague Carlo, who will give you some further examples of the tracking procedure. Thank you.
Okay, so how is this used in Mathematica? Well, we introduced a video object tracking function that can track different data types. In this case, I'm tracking the boxes that were computed in the previous one using image bounding boxes. And you can see if I highlight the result of that, each car has a unique identifier. The tracking knows about which car is which. Video object tracking has multiple input types. It can work on bounding boxes as rectangles or points or label matrices. Here I'll show, there's a quick example that shows tracking on a video using label matrices. This is the original video. This is the track video. You can see how the color jumps around much less. If the input is a video, the detection is performed automatically using image bounding boxes. And I'll jump back to the result. And you can see here the result of the tracking, the whole history of each of the tracklets. You can provide a custom detection function if the input is a video. In this case, I'm using YOLO V8 from the net repository, performing the same tracking. And you can see here how this returns a lot of results, and the tracking is very consistent. You'll also notice how video object tracking returns a specific object. It's called object tracking data. It contains all of the history of these tracklets and various properties, which you can extract using the sub-value syntax. In this case, these are all the tracklets. They are the bounding boxes for all the tracklets. You can get positions that are the centroids of those bounding boxes. In this case, you can look at derivatives of those. Again, there's a collection of properties that can be interesting. You can filter for specific keys. In this case, I want only cars numbered 4, 3, and 1. So this object tracking data only contains those. And selection and property extraction can happen at the same times. It also has video-specific properties. In this case, for each label, you can extract the video, the sub-video that corresponds to it. And the data itself can be transformed to different formats. Tabular, which was introduced in version 14.2, is an extremely useful and powerful one. Dataset is supported as well as time series. So that is all. Thank you very much for your attention. Sorry for being a bit late. I'll upload the slides as soon as possible. Now there's a new talk by Shadi about video creation, and later today and tomorrow there will be office hours and the research and development booth. As for Q&A, I saw several questions that are interesting. Could Mathematica create a subtitle in English from a foreign movie? Yes, Video Transcribe has a language option to do just that. Speech Recognize can use NVIDIA GPU, absolutely. It does use AMX instructions as well. It does use the neural processing unit on a Mac. It leverages the Metal API. I see a question about SERT algorithm making use of optic vector flow. I don't think so. It is unrelated to image displacements, but we are planning to update the image displacement function in the next version. Can a tracklet go off the side of the frame and back in again? I think so. Ali, do you have a more specific answer to this question?
No, actually, I think we have to do some test cases. But I think if the object leaves the bounding box, then it's and comes back again. Like within a very short time, then yes, it's reconnected. But if it's as mentioned, that if the tracklet is expired, then no, you get a new object then.
And there's a question about the possible aliasing problems with this kind of tracking. I'm not sure if you mean if in a given tracklet how many ID switches there are. OSCSERT is a very powerful algorithm that minimizes these ID switches. There are a lot of parameters that are available and documented in the video object tracking function that can allow you to minimize these aliasing problems, like occlusion thresholds and things like that. So if there are a lot of aliasing problems for a specific input for video object tracking, my suggestion is to look at the documentation and play with the various parameters available within the method option. Is there an upper limit of how many objects can be tracked? Well, there are speed limits and memory limits. 100,000 objects seems challenging if that is per frame. It would not be challenging if it is total number of objects in a video. it's all a trade-off in terms of memory and speed. Theoretically, I am not aware of a theoretical limit. I'm sure there are practical limits though. I've seen no issues with up to about 1,000 bounding boxes per frame. The limitation seems to, in terms of memory, seems to be more related to number of objects per frame rather than total number of objects. And the timing of the optimization algorithm goes with n squared, n being the number of boxes per frame. And I think that is all the questions. Thank you very much. And I think we can close it here.